Okay, so we were talking about eigenvalues. And there's two definitions. Lambda is an eigenvalue of f, which is a linear transformation from a vector space to itself, if there exists a non-zero vector of v such that f of u equals lambda u. And so this I will sometimes be calling the eigenvalue equation. We'll have another form for it. It's also the eigenvector equation, so I could perhaps just call it the eigenequation. Call this eigenvalue equation. So this is the definition of lambda as an eigenvalue of f. And u is an eigenvector of f corresponding to lambda if it satisfies the eigenvalue equation, f of u equals lambda u. Right? That's defining an eigenvector of f corresponding to lambda. So the only difference between these two really is that here the focus is on the eigenvalue, and we don't care what u is. We just care that there exists a u. There exists an eigenvector. Here the focus is on the eigenvector and the one that corresponds to lambda. And we had a couple of different characterizations of that. So you can rephrase this eigenvalue equation as f u equals lambda times id v times u. And we argued that the space of linear transformations from a vector space to itself is itself a vector space. I can add and subtract. And so I can construct a linear transformation f minus lambda id v. That's another perfectly good linear transformation. And another way of stating the eigenvalue equation is then that f minus lambda id v times u equals the zero vector. And this is a nice way of stating it because while this is something that involves a vector, an operator, and something else on the other side, this just is kind of a statement about a single operator. And that's easier to work with for a lot of purposes. We saw, for example, that lambda is an eigenvalue of f if and only if this operator, f minus lambda times the identity, is not injective. Right? For it to be not injective means there exists a non-zero u such that when I apply this operator to u, I get 0. It has a null space. Right? Has a non-zero null space. That's true if and only if that. That's true if and only if because injective and surjective collapse to be the same thing in the context of endomorphisms. If and only if this is not surjective. If and only if f minus lambda id v is not invertible. Or I could have also said isomorphic. Now this thing, if I think about fixing lambda, and looking at all the eigenvectors, I could define the eigenspace, which depends on a map and an eigenvector of that map. And that's the set of all u in V such that the eigenvalue equation is satisfied. Right? F of u equals lambda u. That space is a subspace of V. Why is that? It's easiest to see when you think about this characterization here. equal to the null space of something. Of this, right? It's just a set of all vectors such that f minus lambda times the identity of that vector is 0. That's exactly the null space of this operator. And therefore, we know that the null space is a vector space and is a subspace. And that's an illustration of why thinking about this is nice, right? Because now we can talk about the null space of this and the range of it, and we can use facts that we've learned about those objects. So let's prove a few theorems about how eigenvalues and eigenvectors interact and what they tell us about a linear operator. So the first of those is this one. Suppose f is a linear transformation from V to itself, lambda 1 up to lambda m are distinct meaning they're unequal if they're not the same. Eigenvalues of f and v1 up to vm are the corresponding. So while we could define eigenvalues using this, there exists a u. To define the corresponding eigenvectors, I start with lambda, and I make sure they satisfy that definition. These are the corresponding non-zero eigenvectors. And the conclusion is that these VIs that correspond to the distinct eigenvalues are linearly independent. Okay. Let's do the proof. Proof is by contradiction. So suppose v1 up to vm are linearly dependent. Okay, we're going to start here. We're going to need to do one of two things. We're either going to write a linear combination or we're going to use the linear dependence lemma. So let's go with the latter type strategy. Well, let's say it this way. Take the least k such that I can write the vector vk. Since they are linearly dependent, there exists such a k that's such that the vk is in the span of all of the vectors that came before it, v1 up to vk inclusive. Exclusive, k minus 1. So I've sometimes written that as span of v less than k. Okay. Since vk is in that span, I can, of course, write it as a linear combination. K minus 1, vk minus 1. And then apply f. And f is linear, so I can push left through the sum. I can push f through the scalar multiplication. A1 f of v1, a k minus 1 f of vk minus 1. Now, since vk is equal to this sum, if I multiply vk by a constant, I multiply that side by a constant, they're still equal, and I can subtract them. So let's pick a good constant, lambda k, multiply vk by lambda k. That's equal to lambda k times a1 v1 up to a k minus 1 vk minus 1, because this thing is just equal to vk. I can add a negative sign, and they're still equal, so I can subtract this from both sides. but f of vk is equal to lambda k. So this is a way of getting 0 on one of the sides. I'm trying to get a 0 so I can talk about linear dependence and independence. Okay, so now 0 is equal to whatever I get on this side. Okay, but a1 f of v1, so f of v1 is lambda 1 v1, f of vk minus, all of these are lambda k minus 1, vk minus 1. So multiplying, performing that substitution and subtracting, I get that 0 is equal to a1. The lambda 1 appears positively, the lambda k appears negatively. So it's lambda 1 minus lambda k applied to v1 plus all the things in between up to a k minus 1 lambda k minus 1 minus lambda k vk minus 1. Okay. Great. So now we've sort of got our other trick for thinking about linear dependence and independence, which is we've written a linear combination, which is equal to 0. Now these v1 up to vk minus 1, because this was the smallest k that this was true, it must be that all of the vi's that come before it are independent. Right? So this implies that v1 up to vk minus 1 are independent, because otherwise I could have taken a smaller k. Right? If there was any dependence. Okay, so these are independent, and they're equal to 0, so that means that all these coefficients have to be 0. But we assume that the eigenvalues were distinct, so we don't get any zeros here. Right? This thing is not 0. This is not 0. So it must be that all of these coefficients are 0. Okay. And so that's going to contradict the dependence. Okay, so this has a corollary. Which is that if I look at a linear transformation, a finite dimensional vector space, an operator, it can't have more than the dimension eigenvalues, distinct eigenvalues. Proof. Well, suppose it has m distinct eigenvalues. By the theorem, there exists v1 up to vm independent in V. But because the length of an independent list is bounded by the dimension, it must be that m is less than or equal to dim v. Okay, so earlier we reviewed some facts about polynomials, and I mentioned that we can think about the motivation for that was because if we have a linear transform, well, okay, so first of all, if we have a linear transformation from one vector space to another, this is a vector space, so we know how to add these things if f and g are in there, and we know how to scalar multiply them. So that's in this space. Alpha of v is in L of vw. And we can compose them provided that the composition is allowed. And that composition is not necessarily commutative. Okay. So now when we specialize to the case of endomorphisms of V, now composition is always allowed. So I have a multiplication. But it's still the case that G composition F is not in general equal to F composition G. But if we specialize again to only one thing, so just F in LV, and we think about composing it, okay, now we're just saying F composition F equals F composition F. So it's commutative in a completely silly way. And that means we can write this as just F squared. Right? We don't have to worry about the order. And similarly, so F squared is in LV, F cubed is in LV, and so on for any power of F. we're also allowed to add and scalar multiply. So that means that given any linear combination, all equals 1 up to m, alpha I f to the I. Right? It's just some power of f, some scalar multiple of that. That's still a linear transformation, and some of those is still a linear transformation. So that defines a linear transformation in B. So that tells me that given any polynomial, I can apply that polynomial to a linear transformation and get something that looks like this, right? I get a new linear transformation. So why is that interesting? Well, it's because it now allows us to use anything we know about polynomials and figure out how that translates into linear transformations, right? I can take f and I can think about polynomials in terms of f, and I can ask questions like, well, which polynomials are 0 for f? How does the polynomials factor? Things like that, and use that to explore the properties of f. Every property of a polynomial, in some sense, is going to translate into some property for f. First consequence of that point of view is the following theorem. Every operator, so that is f in LV, on a finite dimensional, non-zero, complex, and the complex part is important, vector space has an eigenvalue. So for example, wouldn't it be a good true-false question to omit the word complex and see if that was still true? Let me give you a counterexample. The linear operator of rotation in the plane, a real plane, has no eigenvalue, right? There's no vector that gets sent to a scalar multiple of itself. Every vector is sent somewhere else if the rotation is non-trivial. Right? So if I think about it as a complex in the complex, C2 or something, that wouldn't be true anymore. So it's very special about the real numbers. For the complex numbers, it does always have an eigenvalue. And the proof works because factoring a complex polynomial is simpler than factoring a real polynomial. Okay, so the core idea of this proof as well is interesting. So take a vector and a linear transformation. So take a vector which is non-zero in V, and take our linear transformation f in L of V. Now, with that little information, a vector and a linear transformation, I can construct a whole bunch of vectors. Namely, I could take, the vector v, I could take a big list of vectors. Vector v, f applied to the vector v, f squared applied to the vector v, and so on. Now let's take it up to f to the dim v applied to the vector v. Okay, that's just a list of vectors in V. Could this list be linearly independent? No, it can't be linearly independent because there's dim v plus one of them. 1, 2, 3, up to dim v plus 1, right? And the length of a linearly independent list is upper bounded by the dimension. So this has this many vectors. And so by the definition of linear independence, there exists field coefficients not in zero, not all 0, such that we can write 0 as a linear combination of these vectors. These are just some vectors, right? Well, okay, but this linear combination looks a lot like a polynomial, right? should scream for a second. Okay, I started this indexing at 0, not at 1. What do I mean by that? F to the 0 has to be the identity transformation. Empty product of 0 things. So that's just a way of saying vector v. That's it. F0 times v applied to v. Okay, so now let's forget for a second that we're talking about, ignore the v, and forget for a second that we're talking about linear transformations. Just use the fact that, as we argued here, when I just have a linear transformation and I don't know anything else about it, it's the same as talking about the polynomial ring. Those two objects are isomorphic, right? So doing that, here, this part of this, without the v in it, is just some polynomial p of x. And by the fundamental theorem of algebra, I can factor it. P of x is c minus lambda 1 up to, or x minus lambda 1 up to x minus lambda m for some lambda 1 up to lambda m if it's degree m. Okay, but this is just an algebraic identity. It doesn't matter what I think of my x to be, so it also holds with f in there. And that means that I can factor this thing, right? So that means that 0, which is the sum fiv, n, this sum goes up to the dimension of v. This number here is the dimension of v. That sum has a factorization, c times f. Instead of x, I write f minus lambda 1. Instead of lambda 1, I write lambda 1 times the identity. F minus lambda 2, I'd v. Let's continue down here all the way up to f minus lambda n, m, identity v. I guess this should have been n. Well, yeah, m, that's fine. M equals dim v. And that's applied to v. So it's just a big product of linear. So all this, okay, so this is just some composition, right? I can think about this as being c times f1, which is I'm defining to be this linear transformation composed with f2, which I'm defining to be this linear transformation composed all the way up to fm. So just a composition of a bunch of linear transformations, and then that's applied to v. And somehow that gets sent to the 0 vector, right? And c is not 0. So it has to be that one of these linear transformations, at least one of these linear transformations, takes whatever its input is. Maybe that's fk plus 1, fk plus 2, and so on, of v, put many close parentheses, takes whatever its input in, which is just a vector, and sends it to 0. One of these things has a null space. One of these things has to be responsible for killing v. And so that means what? That means, unpacking it, it means that so f minus lambda I times the identity, lambda I I'd v, is not injective, has a null space. But that means that whichever one is the culprit, there exists one that's the culprit, and therefore that's this thing, this lambda I is an eigenvalue because it satisfies the eigenvalue equation. So we show that there exists an eigenvalue. Now he hasn't told us what the eigenvalue is. We still have no idea what it is in the sense, except that it's, in the abstract, it's this lambda I, the first thing that kills it or something that kills it, but it doesn't actually tell, I can't tell you that it's 5 or it's 3 or whatever, right? It doesn't give me any numerical answer, but it shows that it exists. Okay, so you'll recall that one of the reasons that we're interested in eigenvectors to begin with is this idea that in the best possible case, right? The best possible basis for my linear transformation is one that's going to make all the diagonal elements equal to some constant and everything else 0. Right? Because it's a choice of basis that gives me a diagonal matrix. Now, remember that we're in L of V, so we only have one vector space. We have one basis. So our matrix is square, a matrix of linear transformation. MB of F is square. It's dim V by dim V. And the rows and the columns have the same labels. So we have some, the best way to, given any linear transformation, however we're given it, we want to find a nice basis for it. And one way, of course, that we're actually given linear transformation sometimes in practice is that we're given a matrix, which is not nice. It's just a bunch of numbers. And that doesn't tell us much about it. It doesn't tell us what its eigenvalues are or what any of its invariants are. And we'd like to somehow decompose it or change it. So we'd like to change it around, think about how we can get into a nice form like this, or how as close to this as we can get. Right? So that general agenda of taking an object like a matrix and trying to find a nice form for it, reduced row echelon form or QR decomposition, whatever. Different types of decompositions exist. Trying to do that is a big endeavor, of course, in numerical methods and in other parts of math. It's given something, you want to try to understand how to break it up. And so we're going to try to do what we can to find nice bases for the linear operators that we get. The first kind of nice basis that we want to look at is something which is weaker than diagonal. Eventually we'll get to which matrices we can turn into diagonal ones. But first let's think about getting something not quite as nice, which is upper triangular matrix. Matrices. So first, obviously, so what do I mean by an upper triangular matrix? So if it's n by n, I just mean a matrix which has something on the diagonal and above the diagonal, and it's all zeros below the diagonal. So that's easy to say. But I'd like to say that in a way that talks about the basis itself and not about the way that I've written it on the board. So first what we should do is try to think about what exactly an upper triangular matrix is. So one thing we can do is to say, well, the first step should be thinking about a matrix Vn. And we can just look at one column or one row. So if we just look at the first column and we ignore what's happening everywhere else, we'd like something like, well, let's put a number here and then zeros everywhere else in the first column. And for the rest of the matrix, we don't care what happens. That's kind of a first step toward an upper triangular. And then we want to kind of iterate the logic behind that to build something which is upper triangular everywhere. So let's characterize what it means to be upper triangular, and then we'll show that every matrix, every linear operator has a basis which makes it upper triangular. And that will be the last theorem we have before the exam. Okay. This is a proposition, but I'm not going to give the proof, because the proof is just kind of, you have to just think about it, and then it becomes clear. There's no real argument to make. Suppose F is a linear transformation. B, V1 up to Vn is a basis for V. Then the following are equivalent. But the matrix in the basis B for F is upper triangular. meaning this definition. Secondly, and here's where I have to think about it for a moment. If I take an input vector, I take a vk, and I think about what happens. Vk input, I have a vk output. F of vk, so whatever f of vk is, it's going to be expressible as a linear combination of the basis elements v1 up to vn. And for it to be upper triangular means that it has to be expressible in terms of the basis elements vk and all the ones that come before it. Right? Vk is here, vk and all the ones that come before it. So in order for it to be upper triangular, for each input, this is the coefficients of the output, and they all have to lie above the diagonal, inclusive. So what that's another way of saying that is that this f of vk is in the span of v1 up to vk inclusive for each k. K equals 1 up to the dimension. So there's kind of this nesting happening. To make that a little bit more precise, what's nested? Well, what's nested is invariant subspaces. It is for any k that I choose, the span of the vector is v1 up to vk. That creates a subspace. And this first rule means that I need to send every vector in that back to something which is in its span. So that's saying that the span of v1 up to vk is an f invariant subspace for all choices of k. So we have the dimension of v nested subspaces. And that's what it really means to be upper triangular. Nested subspaces spanned by the span of these, the span of these, the span of these, the span of these. There's not really any proof because it's just sort of thinking about what a matrix is. Okay, so now what we want to do is iterate that to show that we can always get an upper triangular matrix. So though we can't always get a diagonal matrix, it is achievable to always find a basis which is good enough to give us a upper triangular matrix. Suppose V is a complex vector space. And F is an endomorphism of V. Then F has an upper triangular matrix. In some basis of V. And we'll construct a basis, or sort of abstractly construct a basis. So what's the proof? The proof is by induction on the dimension. When the dimension of V is 1, we know what the linear transformations of a one-dimensional vector space to itself. It's just scalar multiples. Okay, so that's upper triangular, very trivially. Right? Okay, so suppose that the dimension is bigger, so that's our base. Dimension is bigger than 1, and it holds for all smaller dimension. So that's our induction hypothesis. That is, if dim v is small, if for any smaller dimension, there exists a basis to make any matrix upper. Every matrix has a basis which makes it upper triangular. Every linear transformation. Smaller dimension. Okay, so by our previous theorem that used the properties of the complex numbers and the fact that we could factor and write this polynomial, like dependence polynomial, as a product of linear factors, one of which had to have a null space, we know that f has an eigenvalue. Call it lambda. And since it's better to talk about things like this, let's take our operator, which has a null space, because f has an eigenvalue. And instead of considering its null space, let's go in the other direction and consider its range. And let's just call that u. OK. So f has a null space. And so it's not injective. Since it's an end, so this map is not injective, right? And so it's also not surjective. And so that means that U is a proper subspace of V. The dimension of U, dimension of the range, is less than the dimension of V. OK, but when we first talked about invariant subspaces, we argued that given any linear map, the range of that map is invariant. Right? That's one of those subspaces which is always invariant. Great. So that means, what do we have? We have an invariant subspace, an F invariant subspace. U, which is smaller, strictly smaller, of smaller dimension than V. So we can consider our map F, our linear transformation, restricted to U. Scans it back into U, and that's just a linear transformation from U to itself. But that's lower dimensional. And so we can apply our induction hypothesis to assume that this map, at least as far as U goes, has a F restricted to U, which you can sort of think of as a block of this, right? So yeah, I get rid of the V1, and I just think of this space. This FU has a basis, making it upper triangular. There's a basis. This F restricted to U has a basis that makes it upper triangular. And then we just need to show that we can extend that basis to the rest of this space. So it has some basis U1, UM, making F restricted to U upper triangular. And we extend U1 up to UM to a basis of V. So say U1 up to UM, V1 up to Vn. And then F of Vk is F of Vk minus lambda Vk plus lambda Vk, stupidly, equals F minus lambda times the identity, not so crazily, of Vk plus lambda Vk. And here we have something by our previous argument that can be placed in the span of U1 up to UM. So F of Vk is in the span of U1 up to UM, V1 up to Vk.